Hi, my name is Josh Griffin.
I'm David DeCoste.
I'm Mitchell Dennis. We are juniors at Oregon State University studying electrical engineering.
We built a self-charging robot that will be able to navigate autonomously and create a floor plan of the room. The requirements for this project included: when the robot is placed within 5 feet of the charging base, it will be able to find its way to the charging station without human intervention. The robot will be able to run for over 10 minutes. The robot can produce a map of the room within half a foot of accuracy. We will have a real-time display that will show the robot's current position and the map the robot has produced. The robot uses LiDAR, computer vision, and SLAM to complete these tasks. What we are doing is applicable to modern-day robotics. Self-driving cars and robots that can retrieve items in a warehouse use the same technology that our robot uses.
There are three main components in our design: the robot, a laptop, and the charging station. The robot connects to a Wi-Fi network, and we use the laptop to remote access the robot and to initialize and display the mapping process. The robot then surveys the room and collects distance measurements via LiDAR. These measurements are passed to the mapping module. The mapping module uses the LiDAR scans to generate the map. This map is output to the laptop display and the navigation module. The navigation module uses this information to coordinate the movements of the robot. An Arduino detects when the robot's battery is low, and the navigation protocol begins to seek out the brightly colored charging station. The navigation block receives information on the location of the charger from the computer vision block. This information is used to calibrate the docking procedure. Navigation sends these commands to a microcontroller that converts the motor speed messages into motor control signals. Once docking is complete, the charger draws power from a nearby outlet and charges the batteries.
Pictured are the charging base and actual robot itself. The enclosure of the robot had certain requirements to be fulfilled. The robot must have no loose components inside its body. That is, it can be shook with nothing loose rattling inside. It also had to be pleasing to the eye. We chose the base to be cylindrical so that the robot would be able to connect to its charging points at multiple angles. It has 2 copper tape strands outputting 12.8 volt DC to the robot. The colors on the base are there for the robot's computer vision. We needed the base floor of the robot to have a lot of area, as to fit all our components inside, namely the Jetson, which is 127 millimeters by 127 millimeters. The camera and the LiDAR both need a clear field of vision as well, so we added clear panels on top so that the camera can see. The LiDAR sits on a platform on top of these panels, so it also has a clear field of vision.
There are 2 parts to consider when planning out how we will power our system: the charging base and the robot. Each subsystem has internal components that will allow it to be powered. Our charging base can plug into the wall and will convert AC to 12 volts DC. We are using a DC to DC converter inside the base to boost the voltage from 12 volts to 12.6. The DC to DC converter allows us to fully charge the battery pack, and it also provides current limiting. We use copper tape on the outside of the base to allow the robot to connect to it on contact. Power enters the robot through 2 metal contacts that protrude from the front of the robot. We are charging and discharging the batteries through a balance charger. Energy is stored in a LiPo battery pack. The motors are powered directly from the output of the batteries. There is a DC to DC converter inside the robot that can regulate the changing voltage from the battery pack to a constant 12 volts for the Jetson. We designed a custom PCB to connect our modules together. We created a schematic and routed our board in KiCad. The board was then sent to Osh Park to be manufactured. Having a custom PCB reduces the amount of loose wires that are used. This reduces the distance that current has to travel from one component to another.
Our robot must coordinate input and output from multiple sources in order to achieve its goal. We have camera, LiDAR, and battery status signals that must be processed simultaneously. These signals are used to generate the motor signals that navigate the robot through unfamiliar terrain. This requires concurrent processes to communicate information to one another. For this purpose, we decided to use the emerging standard Robot Operating System, commonly known as ROS. In order to communicate our results, we used a networking card to allow the robot to connect to Wi-Fi and transmit data over the internet. ROS was critical to our success because it provided us with a number of irreplaceable assets, such as access to robot-oriented libraries and a system of sharing information between systems. ROS operates on the paradigm of publishers and subscribers. Each process is a node in the system and can publish information to a topic. This topic can then be read into subscriber nodes. We used existing libraries to facilitate LiDAR, SLAM, and visualization. We developed our own libraries in Python to coordinate navigation, computer vision, and motor control. While ROS has many advantages, it also has a significant learning curve due to the breadth and complexity of the environment. This was in part what led us to develop original implementation for navigation. Mapping is achieved via the ROS packages RP-LiDAR and Hector SLAM. RP-LiDAR pulls the LiDAR data stream and publishes the 360-degree distance data as a ROS scan message. This laser scan is used by both mapping and navigation. SLAM stands for Simultaneous Localization and Mapping. This algorithm is capable of both creating a map and identifying the location and position of the robot from only the scan data. The map is visualized using the package rviz, which is then accessible to the laptop via a remote desktop client. OpenCV is used to facilitate color-based identification. The charger is marked with a red, green, and blue identifying pattern. This algorithm filters the raw image into its pure red, green, and blue components. Then, the average horizontal position is calculated for each color. If the average positions are within a tolerance of one another, the average of the three values is reported as the location of the charger. If the average color positions are outside of the threshold, then a "not found" message is published. This charger heading is used to provide feedback during navigation. The system takes inputs from the LiDAR scan, battery monitor, and the SLAM output. The navigation module outputs velocity vector commands to the motor driver as published messages. The system has two main modes: find the charger, and find the center of the room. We want to find the center of the room because it provides us with the best point to gather scan data, as well as the best point to find the charger. The protocol is as follows. If the battery is low, look for the charger by rotating in a circle and searching the video stream for the charger. If it isn't found, travel to the center of the room and perform another circular scan. If it is still not found, pseudo-random movement is performed. If the battery is okay, the robot proceeds to the center of the room and gathers mapping data. Coordinated turning is executed by using feedback from the position data generated by the SLAM node.
Everyone in the group consistently showed up to scheduled meetings that we planned ourselves or scheduled meetings with our instructor, Don here. The meetings were helpful to discuss progress, next steps, and how to go about those steps. We even would all show up to impromptu meetings if there was a need. Communicating with each other remotely was all done through Telegram and Skype. The Skype calls were mainly used to set up the remote access to the Jetson. We used Telegram to send links, documents, and have general discussion. These mediums of communication were essential to our success as a group. We would like to thank Sam Ordonez for help on the design and implementation of the robot's enclosure, Dewey Wen for early design advice, Don Here for consultation throughout the robot's design, and Harlan Waldrop for helping us with technical issues. Thank you.